This $4,000 AMD desktop has no dedicated graphics card inside it at all. Instead, the Ryzen AI Halo developer box is a 1.2 kilogram mini PC running off a single USB-C cable, and AMD claims it can hold massive 200 billion parameter AI models locally. It pulls this off by letting the processor cannibalize up to 96 gigabytes of its shared memory pool to use as VRAM. But because the system relies on raw integrated compute rather than a massive graphics engine, we have to test how it handles actual work. A standard discrete GPU gives you a fixed VRAM budget, so if your model and its context window exceed that limit by a single megabyte, it fails to run. That is a hard cliff, but a shared memory pool turns that cliff into a slope, because this platform comes with 128 gigabytes of unified LPDDR5X memory running at 8,000 megatransfers per second. So instead of hitting an out-of-memory wall, the chip dynamically hands up to 96 gigs of that system RAM directly to the graphics side. AMD markets this setup at 126 TOPS of combined throughput, which sounds great on a spec sheet, but it changes what you're actually buying. You aren't buying a speed demon, you're buying pure capacity, which means the primary question you have to answer stops being whether your model fits and becomes how fast it is once it does. To find out if that trade-off is worth $4 grand, we need to run it through a gauntlet of 4 local workflows, ordered by how hard they lean on raw compute instead of just room. We're going to test local chat inference on a very large model, fine-tuning, image generation, and finally video generation. We'll start with the job it wins, move into the tasks that expose the software stack, and finish on the workflow that reboots the machine. If you fire up LM Studio right now on Windows and try to load a 120 billion parameter open model, you are asking for a workload that physically cannot fit into the VRAM of a standard consumer graphics card, so usually the software just panics before you can even type out a prompt. But because that hardware boundary doesn't exist here, community benchmarkers on Reddit are actually running it, and they're reporting that the model streams at 45 to 53 tokens per second. For a compact box sitting on your desk, pulling those speeds on an enterprise-scale model is just the capacity working exactly as designed. And when you drop down to a Qwen 3 30B model, that generation speed climbs to between 66 and 78 tokens per second. Go even further to a 7B Granite model and you hit 97. If you look at independent llama.cpp testing on a Llama 2 7B model, you can see the hardware acceleration working. Generating on the GPU backend pushes 48.72 tokens per second, which is a clear improvement over the 28.94 you get when the software is forced to fall back to the CPU alone. What matters about this throughput data is that none of it is cherry-picked from an AMD announcement. These figures come straight from independent developers publishing their own runs online. So for conversational inference on big quantized models, capacity alone wins the job outright. This is the part of the stack that is unambiguously good, and it shows exactly what this architecture was built to do before we start throwing harder problems at it. Okay, so conversational inference works, which naturally brings up the next question of whether you can actually train on this thing. Fine-tuning an LLM is a completely different beast, because you aren't just holding the model's static weights in memory anymore. To teach it something new, the hardware has to hold those weights plus the gradients and the optimizer state all at exactly the same time. That 3-part footprint is exactly the shape of problem a very large memory pool suits, which means this box has the physical headroom to be a highly capable training machine. But if you actually go looking for AMD's official tooling to run that specific workload, you are going to be looking for a while, because they didn't build it. The hardware is basically running completely out in front of its own software ecosystem, sort of like a hypercar that shipped before the factory finished inventing the steering wheel. Which is why if you want to run fine-tuning jobs on this platform today, you are relying entirely on a public GitHub repository called amd-strix-halo-fine-tuning-toolboxes. If you check the description, it's just a set of containerized fine-tuning images built specifically for the Ryzen AI 395 Plus chip. It was literally put together by a stranger on the internet, because official support for this workload class just didn't exist yet, which means your entire workflow rests on a repo with exactly 64 stars and 6 forks. It absolutely works, but it only works because someone outside the company saw a hardware gap and patched it with their own code. And that is the reality of being an early adopter on this stack. Sometimes the single most important dependency keeping your $4,000 machine running doesn't actually appear on any spec sheet. So if text inference and fine-tuning are basically just a test of how much stuff you can hold in RAM at once, what happens when the work needs raw compute instead of room? Image generation is heavily compute-bound, meaning these diffusion models are actually pretty small, and will comfortably fit inside the VRAM of an ordinary gaming card, so that shared memory advantage buys you nothing. You're suddenly relying entirely on the throughput of the integrated graphics, and from what people are reporting, independent testing found the iGPU hitting about 60% of its theoretical peak. But it does work, and over on the ROCm subreddit, one user reported that ComfyUI successfully renders images and even speeds up after the first frame, provided you do a clean install following AMD's own instructions. It's entirely functional, but generating a single static frame is mostly just a warm-up for the GPU, and video generation is where the hardware finally hits the wall. When you look at pure throughput, one commenter reported that rendering a short video clip here takes roughly 4 times as long as it does on a discrete RTX 5090. The speed is the least of your problems, because that wait time assumes the machine even survives the render in the first place. The same user reported that pushing the WAN 2.2 video model still caused immediate black screens and full system reboots, completely crashing the box mid-generation. The actual limit on this machine is raw compute and software maturity, finally giving out at the exact same time, taking the whole system down with them, which I guess is one way to free up 128 gigabytes of RAM. Look, if you write off the silicon entirely because of a crash like that, you're missing half the picture. You have to ask how much of what just broke is an actual limit of the chip, and how much is only a date on the calendar. Take Ollama for example, where a documented ROCm issue showed the hardware throwing compute corruption, meaning your model's output would just degenerate into repeated single characters after 4 or 5 conversational turns. And that was just the baseline, because 2 separate Linux side regressions completely broke ROCm on this chip for roughly 2 months. From one video walkthrough at the time, getting the system stable again required hunting down kernel 6.18.4 and pairing it with a ROCm 7.2 nightly build, which is a miserable way to spend an afternoon if you thought you were buying a finished appliance. And even if you did somehow get the stack aligned, it wouldn't necessarily save you on Windows, since some users were reporting that LM Studio couldn't see the allocated VRAM at all. The app would apparently just report a flat 0 when you tried to load a model, making the memory pool you paid $4,000 for invisible to the system. The software floor was shifting so fast that the community consensus on whether ROCm or Vulkan was the correct backend changed more than once inside a single year. Which means every benchmark you read about this machine is really just a snapshot of one specific week of its driver stack. So the classic hardware question of whether a platform is actually good or not can't be answered here without first asking exactly when you checked. That full system reboot from the video generation test is the most useful result in the entire gauntlet, because it draws the exact line for who this machine is actually for. If you read the storage review breakdown framing this platform, you'll see they correctly point out that it's competing directly against the DGX Spark. But Nvidia's box runs exclusively on their own locked-down Linux-based operating system, while this is just an ordinary x86 computer that boots Windows 11 or an AMD Linux image natively. And if you read the fine print, native Windows support is apparently the single most common request from would-be buyers of the Nvidia machine. So for a huge chunk of generalist developers, just being able to keep their normal tools on a normal file system removes a whole layer of friction. But the gauntlet we just ran produces a very harsh buying rule, which is that you choose it for what has to fit, never for what has to be fast. If your daily bottleneck is sustained throughput, or if your pipeline is permanently welded to CUDA and you just need image generations to finish in 3 minutes instead of 12, you're the wrong buyer, and you still absolutely need a discrete GPU. But if you're a researcher trying to test inference on a 120 billion parameter model, or a developer running containerized fine-tuning overnight, your actual problem is size. It lets you run workloads that consumer graphics cards physically cannot open because they hit a VRAM wall and immediately crash. This is a memory machine, and the only buyer who really wins is the one whose biggest problem is capacity. Anyways, that's all folks.